Rajat's poster, and if you haven't seen or read the poster, you can always read it later, or maybe visit his webpage and read what he's doing. However, what I would like to talk about Rajat is something that you may not find it on the internet. So I know Rajat from his birth, being the son of a very close friend of mine. So I know him from his childhood. I very well remember him, attending his first birthday. And I have seen him grow from a young boy with interest in science and mathematics. In fact, we studied at the same school in Komba, in Margao. Rajat did his B.Tech in Electronics and Communication Engineering from NIT Surathkal. And I very well remember in 2005, when we were organizing, HIPC conference for the first time in Goa. He came along to help me as a student volunteer. He was studying at NIT Surathkal at that time. His keen interest in trying to learn new things showed his interest and hunger for research. After completing his B.Tech, he chose to do his MSc Engineering by research at Indian Institute of Science, Bangalore. And I have always been in touch with him and have been witness to his career trajectory. He had a recipient of Goa Scholar Scheme, which is now being called as Manohar Parrikar Goa Scholar Scheme. I visited him wherever he was when he was studying at ISC Bangalore. And during my last visit, I also visited him at MIT and stayed with him. So I have invited Rajat whenever he was in Goa to come and talk to my students at the university. And he was very keen in interacting with the students. So that's something that I thought I will share with the local audience here. He's a 100%, Goan born and brought up, and has interest in politics. He's well-read, and he's always keen to help students, particularly those studying in schools, to get them interested in maths and science. Maybe during his next visit to India, we shall be able to arrange his talk in person. So Rajat, welcome for this talk. And, we will, as Neha mentioned, we'll record the talk so that in future, those who missed can also listen to what you said. And I hand over the mic to Rajat. Rajat.
Thank you for such a very kind introduction. I was not expecting that. It's a pleasure to be here and to join ACM Goa professional chapter and to give you this talk today. The only regret that I have is that I'm not there in person. I was flipping through the slides because I'm having some issues. Wait, let me just tackle that and then I'll start my talk. So I'm going to share my screen again because this was a problem. So you can see my screen, right?
Yeah, it's visible.
Yes, Rajat, yeah, you can see.
Okay, yeah, okay. So again, thanks for a very kind introduction. It's a pleasure to join. So the goal that I have today is to give you an overview of my work here at MIT over the last several years. And this has been a collaborative effort with several students, my colleagues, and my mentors here at MIT. So the first goal here is like to give you an overview. The second is to show you what it is that we have been aspiring towards and to convince you of the large gaps and challenges that are there in developing what I call networked autonomy. So what is networked autonomy? Now, humans have been developing tools for a long time, right? Like from Stone Ages. And as engineers, especially robotics and autonomy engineers, it is largely about developing tools that can ease and automate our workload. So I want you to think of a future that is as follows, where you have a bunch of robots, let's say in your garage or somewhere, where you can just tell them to do something and they'll do things for you. So you can maybe send a team of robots to International Space Station, and they'll cooperate with astronauts there and carry out routine functions, which can be system checks and repair, setting up experiments. And there are a lot of experiments that get set up on the International Space Station, perform routine cleaning operations, and all the other activities that go on over there. Another application is where robots working in hospital with staffs and nurses and patients, and uh, they can help manage patients, manage the inventory, replenish, reorganize hospital inventory, assist in medical procedures, and even maybe support elderly with emotional care and support. Another thing would be like a team of robots helping construction. Say you have prefabricated parts, the robots can help assemble them, ferry construction material, plaster, paint walls, install wirings and lighting, and ensure safety of human operators, which is very crucial in things like construction and mining. So all of this, what I just talked about, is not possible today. But in my view, this is the ultimate tool that humanity can develop. So what I define as network autonomy is a team of robots that can seamlessly communicate, perceive, and interact with humans and the environment over long horizons. This could be days, weeks, years along, and to perform useful tasks. Useful in the sense they're useful to humans in improving productivity. Now, does this seem like too far-fetched a vision? Well, I claim that we are in already early days of network autonomy. So we are beginning to have self-driving cars, although this may or may not happen. But if you do have self-driving cars, then it'd be natural to think of connecting them, because all of them will have some Wi-Fi radios that can, or 5G chip that can talk to a cell station. And so then you automatically have a network autonomy of interacting self-driving vehicles, which can talk to one another, exchange information, and ensure safety, because you can then know which car is going in which direction and where the humans are, and you can sort of actively avoid them. So this is the scenario that I'm talking about. The other is that is also being conceived is International Space Station, which I already talked about, which is, so you have these robonauts and astrobees that are being developed in NASA to be sent on the International Space Station. They've also installed like robotic arms, and all of this you can see working as a team on the space station, where the astronaut would just give commands and a bunch of robots would do stuff for them. Another thing is at the hospital. So this is autonomous bot in a hospital in Texas, basically designed to manage inventory. So it's ferrying and organizing a lot of stuffs that doctors want to be kept in the inventory, medicines and all the hospital supplies. This is an instance of a DARPA organizing a challenge called Subterranean Challenge, where the goal is like a team of robots have to go and navigate and map underground cave and find some peculiar objects hidden in that cave. And this went on from 2020 to 2022. So this is another instance and of. So the picture here is a futuristic illustration, but what they are seeking for is like a construction where where humans are directing robots, and the robots can go and build walls and plaster them, and so on and so forth. So in my view, this network autonomy is a future that's like on the horizon, and it'll take a few decades to get there. But to see what the progress that has happened in the last 2 decades, right? So there have been on two kinds. So one is like we have seen, okay. So one is we have seen development of like really good robot platforms. So this is Atlas from Boston Dynamics. This is Ameka from Engineering Arts in UK. And these robot platforms are now capable of walking, manipulation, navigating difficult terrains, and even have now more realistic facial expressions. And these are designed for the robot to be trained to interact with humans. While this is on the hardware side, On the other side, we have had sort of a revolution with deep learning models, where you can train models with large amounts of data, and you can now do things like object recognition and solve language problems like translation and question answering, which were previously considered hard and just a decade ago. So the development of these platforms is good. It gives you good dexterity, ability to navigate and interact with the environment, but it doesn't give you autonomy. And by autonomy, I mean the robots still do not know high-level planning and high-level perception. So the at-last robot can walk by avoiding collisions, but if you tell him, go fetch me my cup of coffee that I left in the kitchen, it wouldn't know what to make of that. So autonomy still remains elusive. And this can be attributed to many reasons, including the fact that robots operate and act in the real world. So the actions have consequences. And for example, incorrect perception can lead to fatal consequences. So a self-driving car that does not detect a pedestrian can go kill the pedestrian. And that's not an outcome that we would want. Secondly, real world is not images. So while a lot of progress has happened on image-based tasks, robots operate in a physical scene that has geometry, and it also abides by some physical laws. So you have to think about those. Thirdly, real world is also not just written in spoken words. It is language and the physical scene combined. So the robots have to make sense of the language and the physical scene together. And so to operate in the real world, robots will have to build a map of some kind, a representation of the 3D environment that scales for long horizon operations. So if a robot goes for like kilometers in length, it should be able to know what is where and store that map for a long period of time. And then when it comes back, it should know that this is exactly what I saw so many hours ago or so many weeks ago. So that kind of thing doesn't exist. Another challenge is for network autonomy is to figure out how, what and when the robot should talk to one another, what it is that they should exchange. And this is not being worked on, and this is still under like early investigation. And these robots are going to operate in time-changing environments, and they would need to exchange information that is safety critical. That is, let's say that pedestrian is walking over there, so I need to tell this other car to avoid taking a right turn so that it doesn't bump into the pedestrian. So this could be like very useful for safety critical driving as well. So while single autonomy is itself elusive, as I've just sort of tried to tell you, attaining networked autonomy is going to be even more challenging. And this is the figure that I tend to show, where so on the y-axis here is all the robot's expressive power. So the higher you go, the robot is going to be is more interactive, is more dexterous, can do long horizon operation, is safe and resilient. So it's like an ideal point would be like as high. So as high up would be a good robot. And this x-axis is I'm plotting number of robots, right? And what you need is network autonomy to do is like take a robot that is highly interactive, dexterous, long horizon, is safe and resilient to uncertain environments, and then take that capability and magnify it, because with more robots, you have more hands and legs to do stuff. But if I want to summarize the state of the art in multi-robot systems, right? So I see on average like three kinds of things. The first is very dexterous and interactive systems that are capable of good manipulation and skills. Practically, they haven't been employed with like large in a large team. So that's the red curve. So you have highly interactive and dexterous long horizon robots, but you can only get less number of robots for them. On the other end of the spectrum is swarm robotics, where people have really expanded and pushed the limits of how many number of robots you can practically deploy. But they have they are on this y-axis scale, they are low in capability. They are not very interactive. They don't have a lot of capability in terms of being dexterous or have long horizon capabilities. More recently, people have also done this surveying, navigation, active perception kind of task, where the capability on the Y is somewhere in the between the two, red and yellow, and have managed to scale it up to like 8 or 10 robots. So the goal for network autonomy, to achieve network autonomy, would be like to push these boundaries so that we one day achieve this upper green curve. And my work has focused on three specific problems towards pushing this. The first one is related to spatial perception. Here, the goal is to build an actionable representation of the 3D scene environment that can be used by the robot. So that firstly, you have to be able to construct it in real time, and the representation should be such that it can be used for all sorts of actions. So that would be the first thing. And if such a representation is scalable in the sense that it's memory efficient and you can have a robot use that for long horizon operations, then that's a plus. The second thing is what I call certifiable and adaptive models. So the way this comes about is because deep learning models are now increasingly finding their place in the autonomy stack. So any autonomy platform that you build, you'll have some deep learning models in them. The problem with deep learning models is that they can fail without notice. And the goal here would be to develop mechanisms to firstly know when the deep learning models fails, and when they do fail, and you can detect when they're failing, you should be able to adapt those models so that they can start working to meet your pre-specified requirements again. So that's the certifiable and adaptive models. And that will push, in my view, the boundary of what is possible today on this y-axis from long horizon operation and and to be safe and resilient. The other work, the third set of problems that I've dealt with and what I'll also briefly mention is this time-sensitive information exchange. So multi-robots, right, when they operate, they'll operate in time-changing environments, and they'll have to exchange and share information that is time-sensitive or safety critical. And the question here is, how can you design protocols that can ensure safety and by sharing this safety critical time-sensitive information? So those are the three parts that I will focus on, and I'll give you an overview of. And mostly I'll focus on the spatial perception part because that's the most recent one, and it's a work that we are very proud of here. So what's the spatial perception, or what I call scene representation problem? So any robot, right? So an autonomy stack will look like this. So you'll have a bunch of sensors here that will feed in. This could be camera or lidar or a bunch of cameras. They'll all feed in some stream into the robot system, and the robot autonomy stack will usually has like three components. You'll have a perception system, which will build a representation of the scene. And that representation then will be used by a planning module to act on. So a planning module will say, get instructions from a language command saying, oh, get me that cup of coffee that I left on the table. And planning module will then decipher that into like specific actions. Like the robot will have to go from A to B, then from B to A, and then go to, then at this other place called C, there will be this coffee mug, and you'll have to grab that. So that will be the job of the planning module. Once the planning module gets that trajectory in place, the controller will basically use that trajectory and then guide the robot to do actuation so that it can follow that trajectory. So that's roughly how any autonomy stack looks like. And for the scene representation problem, right? So the problem is, from the sensors, how can the robot perception block construct a representation that is actionable, in the sense that can be used by planning module to do all kinds of tasks. And we specifically want this scene representation to be agnostic of the task, so that you can do all kinds of tasks with it, and that you don't have to redesign your robot perception module for a different set of tasks that you may think in the future. So that's the scene representation problem. Now, classically, there has been this SLAM and that is simultaneous localization mapping and 3D reconstruction. What these problems do is basically state estimation. So a robot is moving. You have camera measurement. That is, your camera is seeing multiple images of the scene. You can use them to localize points in the 3D scene as well as the robot trajectory. So what SLAM and 3D reconstruction will do is it'll give you the path of the robot in the 3D environment and the 3D geometry. So it'll construct the 3D geometry as it reflects it. So this is a recent work from our lab. This is not my work, but this is from Luca's group, where it's building a 3D mesh of the environment. And this is the robot pose, and the other is the 3D reconstruction that you see. So this is another work called Vox Blocks, where it's another SLAM and 3D reconstruction, where the 3D environment, instead, in this case, it's a mesh. In this case, you form a voxel grid of the 3D environment. But the thing that we realized when we are doing this is the representation is not scalable. So if you look at the one on the right here, right, which is quite common, it stores the 3D environment as a voxel grid. So what the voxel grid is, you predefine a granularity, let's say delta, and you divide the entire space into cubes of delta cross delta cross delta. And for each voxel, you then sort of put in information whether this is occupied, whether this is a part of a chair, or this is free space. Now, it turns out that's very problematic because it's not scalable. So if you look here, so this would be like a voxel grid of some indoor room. This is not scalable because if my voxel size is delta, and if the total volume that you want to perceive is V, then, and let's say each voxel you want to put L labels, then your memory will go as L times V by delta cube. So what we have built in the last few years is a real-time 3D scene graph. So what a scene graph is that instead of the voxel representation, we'll have a hierarchical representation of the 3D scene. And each layer will have a sparser and sparser representation of the scene. So what do I mean by this? So the lowest level will be what you just saw from SLAM and 3D reconstruction will be like a 3D matrix semantic mesh of the 3D environment. The next layer will be like objects and agents. So from the 3D mesh, it can then detect, okay, this is an object. So you can see bounding boxes here and nodes here for each of those objects. So a chair will be a node, an agent will be a node in the layer 2. The third layer will be like a bunch of places. Now, places nodes are representation of the free space. So every point in this places layer will be like a free space point in the 3D environment. And two places nodes will be connected if any robot can successfully traverse between those two places nodes. Rooms will be aggregation of places nodes. So it'll be like, this is a kitchen, that is a washroom, that is a hallway, etc. And then building. So this is the hierarchical representation that we propose. And the advantage of this over the just having a 3D voxel grid is that you can throw out lower level layers and still retain some information about the room, some information about the scene. So for example, if you're traveling for like weeks together with, if the robot has to travel for long duration, right? Then storing all of this becomes problematic. So you can maybe get rid of the metric semantic mesh layer 1, and you can still retain objects in rooms. So you still know that certain objects are there in that location. So it gives you like natural specification way. So now the question is, how do we construct this? So the lower layer matrix semantic 3D mesh is constructed in the same way as classical SLAM and voxel-based method with minor variations. The objects we can aggregate because if you use a pre-trained segmentation network on the images, then you can project those image pixels onto the 3D, and you'll get colored reconstruction, which is the matrix semantic. And it'll tell you that this blue colored is a sofa, this other red thing is another object. So you can just geometrically cluster them and call them an object, and it turns out to be pretty accurate. So once you have those objects, you need the places layer. So the places layer we form by what is called generalized Voronoi diagram. So Voronoi diagram is basically is a way to get a skeleton of a free space. So let's say this is a toy example here. So the black colored one is the let's say is like a wall, right? And red is the red curve that you see is the Voronoi diagram. So what's a Voronoi diagram? It's a set of all points so that the distance from all from each of these points, the red colored point, to the closest surface. So at least, so let me rephrase that. So there are two or more points that are closest to the wall. So for example, this one, so the red point here will have we'll have 2 points that are closest to the wall. So, so this you can form by using what is called a brush fire algorithm, which is just plotting contours. And the reason why this is useful is because this is like a natural sparsification of the environment. So what you can do is, so if you have the skeleton, right, you can also reconstruct this free space, because from each of those red points, you know what's the closest distance to the wall is. Now, this one is an illustration here of the generalized Voronoi diagram constructed from the 3D mesh, and it looks something like this. It's a bit noisy and has still quite a bit of points. So what we do in the paper is that we sparsify this further based on certain criteria, and we get some places nodes. So that's as far as how do you get places nodes is concerned, which will give you a topological map. And the reason why this topological map is useful is because once you know this, robots can navigate. So from the places, you'll know which objects are closest to the places. So now if you tell a robot that go get me this coffee mug in the kitchen, it can basically plan a path from the graph of places, which is, and that sort of problem is solved already. So how do you get the rooms? Because if you look at the 3D scene graph, right? Let me play this. So the bottommost layer is the matrix semantic mesh. The next layer is set of objects. The layer above it is places, and the layer above is rooms. So rooms are basically spatial regions, right? So what we do is like we form rooms by clustering these places nodes, and this is what we do. So the intuition is as follows. So you'll get a bunch of places. So if you consider an indoor environment, right, which is what you consider in this paper, your 2 rooms will be connected by a door. And now if you start inflating the walls, right, along all directions, then that door will sort of close down, and you'll get places nodes disconnected. So let's say all these nodes in the graph that you see were places nodes. And if you start inflating the walls, which is this thick gray line here, if you inflate the walls by delta, then this door will close, and your places nodes, the remaining places node will sort of cluster. And this becomes like one room, and this becomes like another room for us. That's sort of the idea that we use to form the room layer. So again, finally, so the lowest layer is a matrix semantic mesh, which we get from classical SLAM. Objects are formed by clustering similar points in the matrix semantic mesh with similar semantic labels. Places you form by generalized Voronoi diagram, and rooms you can form by clustering places nodes. And you can keep building this hierarchically, because the next layer is going to be some clustering of room nodes, and the thing above the buildings would be some clustering of building nodes. And you can keep building this hierarchy as you go along. Okay, so why is this efficient? My claim to this was this is memory efficient, and you can intuitively see this. So while if you had to store everything as a voxel grid, right, the memory would go like this L times V by delta cube. But the moment if we replace, if we add the hierarchy, right, now instead of storing the labels for each voxel, we can just store the label for each node in the hierarchy. And that hierarchy itself gives you like an improvement in the memory. So instead of L times V by D cube, you now go to V by D cube plus the number of labels for rooms and objects in buildings. And with the places nodes, because places nodes are now a much sparser representation of the 3D environment, you can even get rid of the V by delta cube in the memory. So this is why this representation turns out to be very sparse and scalable for long horizon operation. So we've used this to construct, so let me go back. So we use it, so the contribution here is in this paper has been a real-time system that can build this sparse representation of the scene in real time. It's sort of the first paper to do that. So now let me show you this part. So the problem here, yet that I have not told you is, so, okay, the robot can go and construct the scene graph, but let's say if it goes for like kilometers a lane and then comes back, there's usually a drift because you would have estimated robot's location to be something, and then there's some noise, and then 5 kilometers, few hundred meters ahead, that there's going to be still some drift. And so when it comes back, the drift adds up. And this sort of problem of uh, is also called as loop closure detection. So basically, when you come back, you need to recognize that you're back in the same place and correct your entire map again. So this is what we do. So usually, so I'll let this video run. So you'll see, so this is a robot going in one of the hostels in MIT. So this is hostel called Sydney Pacific. And so it goes on the ground floor, and then it goes on the first floor, and then it comes back here. And the moment it reaches its original location again, where it started, you'll see the map just correct itself. Oh, I changed that. Let me rerun this. Yeah, so it's going to go all the way up, and it's going to come back. And once it comes back, the entire map, you'll see it getting corrected again. So now it's on the second floor. Yeah, you see that? That point of the flip, so because there was a drift, it drifted away and it couldn't, and that drift caused the entire map to drift. But when it reached its original location again, it could figure out that this is the same place that it had saw and that it had seen at the beginning. It could register. Now, classically, the way this has been done for SLAM and 3D dense reconstruction is that people compared images. So if you see this image and if you see another image that looks like this a long time in the future, you can match the features and sort of register them. But because we have a hierarchical representation, we can now use that. We don't have to rely on just images because images depend on the viewpoint, but the scene graph is not dependent on the viewpoint. So what we can now do is like, we can say that it appears that we are also, not only the images are close by, but also the rooms that we see are very close by, and they are the same room. So then we can also plot the statistics that this room contains same set of objects as this other room, and maybe we have a loop closure, that is maybe we're in the same room. So we can use that sort of intuition to do loop closure detection. It turns out to be much better than just using images. So that's the third edition. This is a thing that we do in our lab. So this is a robot, A1 Unitary. Unitary is A1 robot, and we have our sensor payload on the robot, and we want to navigate it around in our lab space. And what it's showing you here is the segmentation network. So this is the image that it sees, and this is the image with the segmentation. So it's detecting green for the walls, gray for the floors, and all the objects are being detected. And on the right here, you're seeing a 3D scene graph being reconstructed. And this is like in real time. So I'll let this video run. So again, if you look at this, it's constructing low-level metric semantic mesh. It's constructing places nodes. This orangish line is the robot trajectory, and it's clustering the places nodes to room nodes. And you can see the rooms being labeled as R0, R1, R2, and don't have labels as yet. And we'll come to that problem. Okay. So this system of ours has been tested on diverse scenes. So this is simulated environments on humans data sets. So this is on, say, a multi-room office. This is a subway station. The previous one was an apartment. And this is on the on a real data set that we constructed. This is a hostel in MIT. I think this is another hostel in MIT. And these span pretty large environments. I think the area for this is like, the total length for this is like around 700 liters. So it's pretty big data sets for SLAM and scene for constructing scene graphs. So yeah, so this is basically saying the same thing, that we have tested on a bunch of simulated environments, because these days you have photorealistic environments. And the other thing is we have also tested on real, and works pretty well. The last point that I want to talk about on the scene graph side is the structure. So, okay, we have constructed a graph, but graphs are not the easiest thing to handle. And a lot of computer scientists know that most of the problems that you formulate on graphs easily become NP hard, and you need a scalable way to deal with that. So how do you deal with this graph? The interesting property that we noted about scene graphs in particular, but in graphs in general, is that there's this parameter called tree width of a graph. So what is the tree width? So just like graph will have n nodes, or so many edges, or the diameter of the graph, which is the maximum distance between any two nodes, tree width is some such parameter. So given a graph, you can compute its tree width, and it's always fixed. It turns out that most of the graph problems, right, turn out to be polynomial time in the size of the graph n being number of nodes, but exponential in the tree width. And it's known that if you bound the tree width, right, if you know the set of graphs have tree width bounded, then all the graph problems, a lot of graph problems, become polynomial time complexity. So that becomes it becomes compute efficient. So this is a result from a long time ago. It says that, so people used to do this graphical inference as a probabilistic inference on graphs. So basically, you have a graph, and each node in the graph is a random variable, and you know some of those random values of the random variables, and you want to infer the others, and that's called graph inference problem. And this was this NP hard, and it's very complex and things like that. But one of the results was that if a graph is known to have like low tree width, a bounded tree width, then the inference is like polynomial time. But not just that, this paper proved that low tree width is the only restriction that can ensure polynomial time complexity of inference on graph. So there are those kinds of results. So tree width is one parameter which, if you bound, you know that you can get good compute on a lot of problems relating to graphs. And recently, people have also used graph neural networks, but graph neural networks are not very expressive. So for example, I have these two graphs here of 6 nodes. So this one is one graph, this is another graph. And if you start with same features, right, for all these nodes, then no graph neural network can distinguish, can actually tell you that this graph is different from this graph. But if you just do a simple tree decomposition is something that I won't describe, but it's something that gives you a tree width of a graph. So if you just do a tree decomposition, and it's a computation precision, there's no learning here. So if you just do a tree decomposition of this and this graph, it can tell you that the two graphs are different. So, and this has been highlighted in other works, that graph neural networks are not really fully expressive and have certain limitations. So why am I telling you this story about tree width and tree decomposition? Because what we proved empirically as well as theoretically in the paper is that the scene graphs that we are constructing, right, the hierarchical scene graphs, they turn out to have bounded tree width. That is, their tree width remains bounded irrespective of the size of the scene that you explore. And that then allows us to do all sorts of computation, or at least we can say now that with bounded tree width, you should be able to do a lot of computation with scene graphs, and you don't have to worry about the size of the graph. And so one of the things that we did was to use that low tree width to our advantage in developing better, more expressive graph neural network architecture. So I told you about the tree decomposition. So what we basically proposed was that instead of doing message passing on the original graph, which graph neural networks do, you construct a hierarchical tree decomposition of the graph and do a message passing on that. And the problem that we applied it for was the problem that I mentioned, which is the room classification. So remember the real-time reconstruction, we could label each object because it came from the semantic label of pre-trained model, but we couldn't really label room nodes. So we knew this is a chair, that is a table. We also knew this is some room R0, that one is some other room R1, but we didn't know a label for that room R0. We didn't know whether it was a kitchen or a bedroom or an office building. So we used this new architecture using the low tree width structure of the scene graph to have the new architecture that could label us room nodes. And what we saw was more generally is that if you do message passing on the input graph versus message passing on the H tree, it always gave you much higher performance. So that was more of a theory insight, and this turned out to be true for all other cases as well. Like we tested not only on scene graph but other graphs as well. And this is an experiment that I want to show where the robot is going around, but in real time we also have the neural tree, which is the architecture that I just described, being used to label room nodes. So now you'll see the agent is not only going around, it has objects being labeled. Let's say table, chair. It's getting places nodes, but now the room nodes are also getting labeled. R0 is kitchen, it thinks R1 is hallway. Oh no, it thinks are dining room. So it keeps flipping till it sort of finally converges. Okay. So I want to end this the part on spatial perception here. And the main thing is that we're able to get a scalable representation for long horizon networked autonomy. This is scalable in memory, as I described, and it's also scalable in compute because they have bounded tree width. And we now have a pipeline that does real-time scene graph reconstruction. It's called Hydra, and it's available online for free. It's like open source, so you can just download and put it on your robot, and it should work with the camera. Okay, so that's the part about the spatial, the scene representation problem, and how hierarchical scene graphs can solve that problem for single autonomy as well as for network autonomy. The next two parts I'll go over more quickly. The second one is certifiable and adaptive models. And the goal here was that your deep learning models are going to be in your autonomy stack, and those models are going to fail. So safe and increasingly, right, as robots get deployed in the real world, safety is turning out to be a major bottleneck. And for safe autonomy, for the entire autonomous system to be safe, I say that your perception block in the autonomy stack also has to be safe. And by that, I mean a perception block, you have to impose two things. One is when a model fails, when a deep learning model in your perception block fails, you should know that it's failing. And when you know it's failing, you should be able to adapt that model so that after a while, it starts working again. So that's the certifiability and adaptivity requirements. So this is the two research questions that we ask. Can we certify if an output produced by a robot perception model is always correct or not? And when the model makes errors, how can we correct for them and learn from it? So just a deeper look as to give you an intuition of what the solution is. If you look at the perception autonomy stack, and this is what I described before, you have sensors feed in information to the perception builds a map of the environment, then that goes through planning and control. So if you look at where the deep learning models get put into this perception pipeline, is they usually come in like the front end and the back end. So the front end is usually a neural network, and the back end is solving some optimization problem by imposing geometric constraints. And where do these geometric constraints come from? Because we live in a physical scene, right? The robot is trying to see a physical scene. So the front end network will usually operate on images, and then the back end will try to ensure that the geometric consistency between various images and the physical scene that you saw are maintained. And the idea that we propose is that basically to certify whether the neural network is working correctly or not, you can use this geometric consistency constraints that you have for free, because you know it's a physical world, you know it's a geometry. So we propose a way to certify a model. We call it the certifiable model. This is a more abstract result where we show that you can basically certify any deep learning model with like 2 binary valued certificates, which we call observable correctness and non-degeneracy. I won't go through that. What I'll give a review of is the strategy that we use to self-train, which we call correct, certify, and self-train to adapt the model so that it starts working again. And the way the strategy is designed is as follows. So let's say you have a model, a deep learning model that's giving you some predictions. So you'll wrap it around with like 2 wrappers. The first one is called a differentiable corrector. So this is like an optimization problem. They'll try to impose this geometry consistency constraint so as to improve the model prediction. Once this improves the model prediction, the certificate will basically check again with some geometry consistency constraint whether the output and the input match. If the certificate says it matches, then you can basically use those as pseudo labels and retrain the model. Now, once you retrain the model, this is now a different model and giving you slightly better predictions. You can again use the differentiable corrector to further improve the predictions. Then again, using certificates, you can get pseudo labels and you can keep cycling on this loop, and your model, and hopefully your model will sort of match the criteria that you have. And we applied this for a particular problem which is of interest to us, which is called object pose estimation. So object pose estimation is basically seeing how the object is in the 3D environment. It's used in various places. For example, in warehouses to pick and place objects on an assembly line, to satellites, you want to know the pose of the satellite so that you can go closer to it or stay away from it. In self-driving cars, you want to know the pose of the vehicles. And more recently, so this is a lunar tower construction where you have an autonomous robot down there, which is trying to assemble prefabricated parts to construct like a tall tower on lunar missions. It's like a futuristic thing, but I'll get back to this in a while. So we implemented 2 methods. I won't go through this in detail. We did it for point cloud based pose estimation as well as RGBD camera based pose estimation. And what we are able to see is like, so this is before and after. So if the before self-training is the blue line, and ideally your line should be like as left as possible. And the red one here is, it assumes like you get like full supervision on the real data, which you don't have. But that is just a baseline to compare. So we see that even if you have a domain gap, which is the gap between red line and blue line, after all self-training, that sort of bridges. So your green line becomes like a blue line. Your blue line becomes like the green line, which is very close to the red line. It's absolute upper bound for these approaches. Okay, so one quick nugget is that the certifiable pose estimation, which has all the certifiability and adaptivity guarantees, is being used for autonomous tall lunar tower construction by this NASA Langley Research Center. They have a nice software design paper out for that. Finally, time-sensitive information exchange. So this was most of my PhD work was on this. And so the motivation was as follows. If you have self-driving cars, right? Now the red car has to decide whether it wants to overtake the truck or not. But the truck, if it informs the red car that there's a white car coming in front of me, then the red car can wait and avoid collision. Similarly, this red car, if it wants to take a ride, but this white car informs it that there's a pedestrian crossing the street, then it can sort of be better informed to wait and maybe save a pedestrian life. So that was sort of the motivation. And so in exchanging time-sensitive information can lead to safe and resilient behavior in network autonomy. And that is what we're aiming for. And what we realize is there's this metric called age of information, which is the time since the last received update. I probably won't go through that, but it goes as follows. So it linearly increases till you receive an update. And once you receive an update, it jumps down to the age of that update. And the age of the update is the time since that has been generated. And typically the age curve looks like this. And the reason why we're interested in, we're looking at a problem of collision avoidance for autonomous systems where, so consider A, B, C to be vehicles. And if B is moving with some speed V, right, and it's been some delta B time since you have received information from B, then B can be anywhere in this yellow region. And similarly, C can be anywhere in this yellow region. And what we wanted to analyze was how often can A, avoid this net yellow region. And it turns out this yellow region, the way it behaves is some nonlinear function of this age. And so we started analyzing age. So this is just a summary of work. So we started first with like studying policies that could minimize age for single hop wireless networks of autonomous agents, and we proposed a bunch of policies. So these are the first set of works to do so. Also, this led to good tools that people could use to analyze and design policies for minimizing age of information. And then that got recognized by the community, as well as was published as a monograph. So you can check that out. More recently, we have, and incidentally, this was my earliest work on age was on multi-hop wireless network. And the reason is the Wi-Fi and cellular systems, right? They mostly operate on single hop. So your phone directly communicates with your cell tower, or your Wi-Fi laptop communicates directly with the access point. But when robots, you operate them in wild and you have a network of robots, then there won't be a base station. You'll have still multi-hop communication. And that was an important problem. Multi-hop communication is a big problem even today, because when you have multiple hops, you can lead to a lot of outage problems. So we started with that, investigating that in 2017. And in 2022, we managed to very cleanly solve it. And I think these are the set of policies that we proposed in that paper. So check that out. This is just an overview. One final insight that I want to give about age is, when he started writing on age, there were a lot of questions. How is age different from delay, or how is age different from latency? So I wrote a paper in, so this came out on transactions in 21, but this was there in 2018, 19-ish. And the thing that I showed was age is not same as delay. That is, you can have systems, communication systems, where if you minimize for age, you can have the worst case average delay, but you can also have worst case delay variance. And this is sort of the plot that I had. So you plotted delay on y-axis and age on x-axis, and these are all the things that you could achieve. So the lower the age you get, your delay went high, and vice versa. Okay, so I lined here. I'll just summarize. So we've seen three aspects of pushing the boundary of network autonomy. One is spatial perception. We proposed hierarchical 3D scaling graphs as a scalable representation for single autonomy as well as network autonomy. Certifiable and adaptive models that can probably ensure safety for perception models, and time-sensitive information exchange for multi-robots to share safety-critical information. So I'll conclude here. So this is the aspiration. The red, orange, and yellow is what is feasible. And this is the work that I've done to push that boundary. But there's like a huge gap from here going all the way up to network autonomy and what I talked about. So I want to finally say that this is like joint work with like a lot of people, a lot of students, colleagues, and mentors here at MIT. So it's everybody's work, and thank you. And before I close, I want to say a big thank you to ACM Goa chapter for organizing this set of events, as well as doing all sorts of things in education. I see them, I hear about them, and it would have been great to have some such things when I was growing up, but you all are doing it now. So all the power to you and all the congratulations to you. So I'll end here. And I'll take any questions if you want.
Yeah, thank you, Rajat. I'll now invite Sheetala Prasad to handle the question answer. Yeah, Sheetala.
Yeah, hi. Thank you, Professor. Yeah, hi, Dr. Rajat. So thanks for the wonderful talk, and we had so many insights, stories, and all. You showed us so many visual results as well as the qualitative results. So thanks for everything, all the things. So first of all, I'd like to ask in case if in our participants we have any questions, we'll take that first. Yeah, so there is one Vedam. So maybe you can unmute yourself and ask question.
Yeah, am I audible?
Yes.
Yeah,
yes.
I can hear you. Yeah.
Hi, Dr. Talak. Great talk. I had a question about C3O, where you mentioned the difference. You mentioned a differentiable certificate, I think. If you could go back to that slide. Yeah. The other one was okay.
This one?
The
I
certificate.
think there was
Okay.
the three things in the loop.
Right.
But I think this right. So is this like a loss that you are imposing on the model in parallel to whatever normal KL loss or something be doing? Is it something like that?
No, so the differentiable corrector is an optimization problem. So it doesn't. So let me maybe give you an example here. So what happens is, let's say we consider the first instance as a key point base. So you have a neural network here that is detecting some key points. Okay. Now, because of the sim to real gap, actually the key point should be like this, but they'll be all over the place because of the domain gap. So what is the domain gap? So it is trained on certain set of images, but it sees something else. So it doesn't know to detect correctly, but sort of approximately does, or maybe doesn't. So we have this corrector, which is like an optimization problem, does this. Basically, what it's trying to do is trying to use whatever geometry that exists in the scene. So in this case, it will try to match the dense point cloud to a CAD model, provided, and you add a correction. So it's sort of a optimization problem. It's not exactly a loss, but it can be construed as a loss, because what happens is you have a differentiable optimization here that gives you some correction, and then your certifier says these are correct, so you can just back propagate through all of that. So in a way, you can think of it as a loss, but it's not exactly a loss, because you can also not do a back propagation. You can train it with pseudo labels. Yeah.
All right.
Did you have something else
If I
in
can
mind?
follow
Yeah.
up.
Yeah.
Yeah, I kind of got it, but then does this mean you're saying I can see now that there's a CAD model in semantic points?
Yeah.
So that means you're having priors for whatever objects you're detecting?
Yeah. So this is the simplest case that we tested it on first. So the mechanism, we were not sure whether it will work. So the one slide that I'm showing you here is key point based pose estimation. So we have CAD models and key points on the CAD models that we can annotate, and then you can train your key point detector in simulation. And we have no real world training data at all, and just deploy it on training, it will not work. And then you do the self-training loop and it'll start working, and you don't need any key point or any such annotations on the real data.
So you're saying you're going to take the CAD out once you put it in the wild for training?
No, for the CAD model base, you need object model. So without a CAD model, right? So your object pose estimation becomes like degenerate, because what is a pose? So it's your object poses with reference to something, right? So you're saying your pose 0 is this pose, which is the CAD model, and then your pose in the wild is with reference to that. Now, this is our earliest work. We have generalized this and to without using CAD model, and that will come out soon. So where we do the same set of correction
do you
for
also,
with like shape and
right? Do you also, in that case, I mean, you must have you in the wild, when you find an object, you would also need to first match it to a certain prior, right? A prior CAD. If you see a sofa, then you need to first know that it is a sofa to match it to that CAD. So how do you deal with that?
So in this case, if you use CAD model, you use the semantic segmentation to tell you that it's a sofa, it's a chair, or whatever. The other case that we are doing is like, you don't need that. You can just take the visual feature and put it to a shape model, and that'll just generate the shape. Now, what we are not solving, and what I haven't solved, is the generalization problem, which you probably have in mind. That is, if you train a neural network on certain set of chairs, can it detect some other chair that it has not seen before? I don't know of a good model that can do that. There are papers that claim it, but it's sort of a bit, it doesn't give you a good reconstruction. That is not the problem that I'm solving. So the problem that I'm solving is, some priors about the object shape and the reference shape, right? And you want to estimate the pose of that. So it is in that limited setting.
I got it. I got it when you said that you're matching it with the model. I'm guessing like in an RTNN way, where you first detect what it is and then you bring in the prior. Yeah. Oh, all right. Thank you very much.
Yeah. So, hi, Rajat. I have one more quick question in this before other students ask any. So I have one question. Like you said, like you are not able to solve the multi-category things, kind of things, right? If you see multiple instances of same category, correct?
Multiple in, yeah, here.
Yeah, the chairs, and if you have a different shapes chairs, then it's difficult. So is it possible for your model, current model, to get rid of multiple views of the same chair?
Yeah. So the thing is, like, I'm not so my design is not this neural network. My design is the corrector and the, so let me go back here. So my design is not this neural network model. My design is the corrector and the certificate and the self-training part, right? And that should work. Now the problem is with the, so we did CAD model based pose estimation because that sort of people know how to do that well. So if you have good training data, you can train it. And the problem that we solve is if you don't have that training, annotated training data, you can use this loop to update it. Now, the question of generalization, which you point out, is like category level generalization, right? You see a bunch of chairs and you see a new chair, and can you generalize? Well, if someone develops a model that can do that, then probably we can put this around it. But because I didn't know of a good model. I mean, there are papers that claim that, but if you start seeing them like investigate then, right? So I was not very convinced that they are doing good generalization. So we didn't go in that direction. What we have gone more recently, however, is object pose and shape estimation. So in that case, instead of a CAD model, what you do is like you have a bunch of CAD models and you can train a shape model. So what that will do is the moment it sees some object, it'll reconstruct that shape because it has seen it before. So it is priors, as the previous question I was asking, but it's a priors in a different way. Rather than using a CAD model, use a neural network model to predict that shape. But it is still a shape that you have seen before in training. It's not generalizing across. Yeah. So we didn't do that because we don't know of a model, and we don't design model. We do the other part.
Yeah.
Does that answer your question?
Yeah,
There
sure.
are a couple of questions in the chat.
Right.
Yeah. Maybe Jay, you want to ask this question by unmuting?
Yeah, maybe Jay can ask it unmuting.
Okay.
Jay, are you there?
Rajat, you can see the question?
So if it's not,
Yeah,
I
I'll
think
try.
maybe I can read it for you. You
Yeah.
mentioned in special perception that you give labels to the room. How does it guess the hallways or kitchen? I missed how do you do it? Is it based on what objects are present in the room or how? So it's the same question
Yes.
like what I was also about to ask. Like you have a B0, then from B0 to room 1, room 2, room 3, how are you going to categorize those things? Yeah.
Okay. So what happens is once you have the rooms, right? What you don't have the labels for the rooms, but you know that the room contains these objects because rooms are just an aggregation of places nodes, and you can from that figure out which objects are closest to it. So given that you know objects in the room, you can basically we train a neural network, and we basically train a graph neural network as well as a neural tree. And the neural tree does better than a graph neural network because it's basically a graph classification task, and there are some limitations for graph neural network to do that. So it's a trained model. So there's a data set, Matterport 3D online, which has like 90 scenes. So we train it on that, and it gives us for indoor room classification.
Okay, cool. Thank you.
Yeah.
Question by Anish.
Yeah, there is another question by Arish. What were the sensors used for perceptions on the Unitary A1 for SLAM? So yeah, that's quite interesting.
Yeah, it's a RGBD camera. Which is it? Yeah. RGBD.
So it's like you mean to say like only RGB sensors are enough to capture those
Yes.
minute details? Like if it is,
Yes.
then how minute details can be captured? Like a cup, or cup's cap, or something. Like how
Yeah,
many details you can do that, or what is the quality of the sensors like configurations kind of thing in case if I ask.
Yeah, that's a good question. So we didn't try like various sensors to sort of see the
Yes.
quality. We had one. So the RGBD camera worked. In terms of quality, right? That turns out to be a problem. So what happens is, if it depends on how the robot is looking at. So if it is looking right in front, it'll be able to get the object. If it's looking from the side, it won't get the object that well. The second thing is for real-time operations, right? You need to fix some granularity, like how many pixels are you going to cover? So if there's like small objects, it will not catch that. So that's a major problem. And that is one of the things that we are attempting now with that object pose estimation. So now with just a small object, just from vision, it'll be able to reconstruct the entire objects. And we almost have that, so it should be out in a few months. But yeah, that's a great question.
Yeah. So it was a little bit curious, but yeah, thanks to answer that thing.
Yeah. So
And also-
Rajat, I have a question. How do you get the voxel representation? Because you're using RGBD camera, right? But how do you
Right.
get the voxel? Yeah.
So
Voxel.
for voxel, right? So there are already preset methods that people use. So I think we started using this thing called VoxBlocks, and there's also VoxBlocks++, which does semantic. So it's basically the same idea. So you do image registration, right? And you can get a pose. So you basically project them onto 3D. So and so you can do that with voxels in the same way, but now you'll feel whether each voxel is occupied or not.
But are you not just processing the point cloud? Are you also considering the mesh to be, the 3D triangular mesh to be generated out of that point cloud?
Yes. So the Chimera stuff, right? So this is not my work, so I'll just try to summarize. So Chimera, what it did was it detected features on the image, and you could form triangles, and then projected that triangles in the 3D. So you had a mesh, and then you can just match the two meshes as you went along. For the VoxBlocks, so for the voxel one, we use this VoxBlocks to get the voxel grid. From that, you basically have the sign distance field, and then you just run marching cubes to get mesh. So marching cubes is like a famous algorithm. You just send, it'll give you a mesh from sign distance field. So I don't think we've invented much there. So it's more like using a thing that is out there. But increasingly these, right, the dense 3D reconstruction, this is also a literature on its own. And it's, there are a bunch of work. People are now using nerves and things like that to do that.
Okay.
There's one more question.
Sorry. Well, there's one more question on, do you use IMU sensors to combine the camera poses?
Yes, we also use IMU sensors to combine the camera poses. Thanks. So IMU, but I think IMU is like optional. I think you can do without it, but IMU will always give you like much better localization.
Okay. Follow-up questions: would it be help to use latent response to remove the CAD model requirement, like in deep SDF or something like that? So yeah, there's one more question by Kamath. Jai Kamath.
So you said that you required a CAD model. Like, would it help to have something like learned latent representations of objects?
Yeah, we're doing that.
Oh,
yeah. So that's a paper that's going to come out. So
excited to read.
Yeah. So the thing is, like, a CAD model is the simplest case, because so there are two problems when you do object perception, right? You want to estimate the pose, but you also want to estimate the shape. But our thing was not the object perception. Our thing was more like whether you can do certifiability and adaptivity of any pose estimation, any object perception model that is given. So we fixed the object shape issue, and we said, let's just go with the CAD model and see in the simplest case that it works, and it worked. So now we are sort of extending that to object and shape. Pose and shape. But the generalization is still open, in the sense that the generalization question that I said, right? The neural network trained on something and then it sees something completely new object. I haven't seen a good model to do that. And yeah, so that is not still a question that is open.
Also, like, deep SDF can interpolate between objects, but you are talking about questions wherein you cannot interpolate between. Like
so a lot of papers claim that, but I haven't found one to my satisfaction that it really works.
Got it. Thanks.
So I think it's almost 6:15. So if there are no more questions,
Yeah, if
yeah, I think let's thank Rajat. Anybody wants to say something?
I had a quick question just
Yeah.
because
Sure.
he mentioned that he's using latent representations. Now I'm a little more curious about how you're enforcing strict geometric constraints on something like a latent representation, which may not be that precise, I think.
Yeah, but you'll still have like a reconstructed shape, and you'll have a pose, and you'll have point cloud, and you have point cloud from different views, and so you can still. So there's still
Does it have
geometry.
the precision that you can impose strict geometric constraints on it?
So there will be geometry, and there'll be noise and outliers. So that is the challenge, right? So that is how you have to frame the optimization problem correctly.
Okay, thank you.
Okay.
okay.
Thanks, Shitala, for handling the question answer. And let's, big applause to Rajat for having accepted our invitation at a short notice and giving this talk. We look forward for hosting your talk when you visit India next. It will be nice to interact with you in person. So thank you all, and we will keep you informed about our next session that we will have through email also. Okay. Thanks. Thank you.
Thank you, Rajat.
Thanks, everyone. Thanks for joining. Bye.
Yeah, thanks.